Welcome to the next lecture in the series on condensed matter theory. In this video I want to talk about electron correlations and how they influence the material properties that we see around us. Now, before we go into a few examples, actually in the next video where we show what electron correlations can do to your ground state and response functions of a system, I first want to spend some time to define what we actually mean when we talk about electron correlations. And when we talk about electron correlations, we will look at theories that go beyond mean field theory descriptions. So we're not talking anymore about electrons moving in a potential, but we have the Coulomb interaction between the electrons that now make your system interacting and correlated. And we have to treat this Coulomb repulsion explicitly into our theories. And what we will see during the next lectures is that this will lead to all kind of new phenomena that cannot happen when you treat your system on a mean field level, and the emergence of new properties of materials that are actually rather unintuitive following from the laws of quantum mechanics. So let's start by just giving you a definition of what we mean when we say our state is correlated. And I very much focus here on states and not just on a system, because one system might have states that are correlated and others that are uncorrelated. And we say that a state or a quantum state is correlated when it is not single Slater determinant representable. Now you can give different definitions, and we will talk about the relations between them. We can define correlations or a correlated state with respect to charge fluctuations, or we can have a look at the entanglement of a state. They all are measures of correlation, and we definitely find that an uncorrelated state is defined in the same way in all these different definitions. And in order to make these comparisons, we will also have a look at a natural basis. So within our definition, we call a state correlated when it is not single Slater determinant representable. So let's have a look at some examples. And for this we need to count the number of Slater determinants that we have in our system. So if we create a single electron out of the vacuum, then the number of determinants that we have is equal to 1. Now if we create two electrons, one in quantum numbers alpha, one in the state with quantum numbers beta, then this is still a single determinant. We can, however, create a state where we say, well, I create one in alpha and one in beta, and I make a linear superposition when I create one in alpha and I create one in gamma, acting on the vacuum. Of course, we want this state to be normalized, so square root of half and the sum of 2. Now the number of determinants that we have in this state is 2. So can we now say that this state is uncorrelated and this state is correlated? And for that we have to realize that we do not say that states are correlated when they are represented by more than one determinant, but we make the statement that a state is correlated when it is not single Slater determinant representable. So the question that we should ask ourselves is there a way that we can rewrite this state such that it is a single Slater determinant? And there is, if we define the state I equal to the linear superposition of B and gamma, then we find that this state, which is square root of half, create particle in alpha, create particle in beta plus gamma, acting on the vacuum, is equal to A dagger alpha, A dagger I on the vacuum, and therefore given by a single determinant. So all three wave functions that I have written down so far are single Slater determinant representable and therefore by definition uncorrelated. Now, can we also write down a state that is correlated? And if you take the state where we put a particle in alpha and a particle in beta, and we make a linear superposition where we put a particle in the state with quantum numbers gamma and one with quantum numbers delta acting on the vacuum. Now this state is truly correlated and non-single Slater determinant representable. So the question, of course, that we need to ask is, well, in the previous example we were able to guess that we can make this linear transformation or this unitary transformation and therefore go from 2 determinants to 1. Why are we not able to do that here? And more general, when we have a determinant with 10 to the 23 particles as you have in a solid on a basis that is even larger, 100 times 10 to the 23, how can we find those linear combinations? And how can we answer the question if that state is single Slater determinant representable or not? And for that, we will define the natural orbitals. And this is a concept introduced by Leudin in the 60s, 1956, a bit earlier. And when you talk about an atom, you talk about orbitals. When we talk about solids, we have Bloch states. So instead of talking about natural orbitals, I will talk about natural states. So how do we define the natural states, the natural one-particle states, because that is what orbital has the advantage over states. How do we define the natural one-particle states of a system? And there we should say of a wave function, of a state. So the natural one-particle states of a many-particle state. And for that we can define first of all the one-particle density matrix. And Ij, which are the elements of your matrix, are given by a many-particle state, and then we look at the expectation value of the number operator. We create and annihilate a particle. If I is equal to j, this just tells you how much that orbital is occupied, and if I is different from j, you say how much can I scatter between them. Now, this defines a basis, or this is calculated on a basis, and our basis is given by the states a dagger I 0, where I can run from 1 up to n. What we saw before, we can define unitary transformations of our basis state and then get more or less determinants. If I go from basis alpha I to alpha, beta and gamma, you get more determinants, or the other way around, less determinants. So let's define a unitary transformation. My states, a dagger alpha, acting on 0, are given by a sum over I, ui, alpha, a dagger I, acting on the vacuum. And this is a unitary transformation. We make a basis transformation. And we do this such that n alpha beta is a dagger alpha, a beta on your many particle states is diagonal. Delta, alpha, beta, and alpha, alpha. With that, we know that a dagger alpha acting on 0 are eigenstates of the density operator. So for a general state, we can calculate the density matrix. We diagonalize the density matrix, then the eigenvectors define a unitary transformation. And if we apply the unitary transformation to our basis, then we will find the natural orbitals of our system. So the natural orbitals are given by these states that have the property that your density matrix is diagonal. Or in other words, the natural orbitals are the eigenstates of the one particle density matrix. Now, how can we use this basis? Well, if we find that the density matrix on a basis of the natural orbitals is given by delta alpha beta, which always will be true because these are the eigenstates of that matrix. And now our eigenvalues are either 1 or 0 for states that are occupied or for states that are empty. What we then have is that our total many-particle wave function is just given by a single string of creation operators on the occupied states and therefore single Slater determinant representable. So if this is true for your density matrix on the basis of the natural states, then we find that the state is single Slater determinant representable. So if we come back to the definitions, then we first of all said that a state is correlated when it is not single Slater determinant representable. We can now turn this around and say uncorrelated states are single Slater determinant representable on the natural basis of the state. And this will always be true. We saw this, for example, in our mean field examples where you calculate the band structure of a material. There we could define Bloch waves or Bloch wave functions, Bloch states. And if your system was made of a single band, then the Bloch states were the eigenstates of the one particle Hamiltonian. The density matrix is diagonal on the Bloch states, and your many particle wave function is given by a string of correlation operators and a single Slater determinant. Now let's have a look at the next way to define correlations. And here we relate correlations to charge fluctuations. So I want to calculate what the charge fluctuations for a general state are, and the statement is that uncorrelated states have no charge fluctuations on the natural orbital basis. So I want to calculate what the variance is of my density matrix. And for this we have our many particle state, and we have the density matrix, and for the variance we take the density matrix squared and we subtract the square of the expectation value of your density matrix. This is equal, I can commute a dagger I and aj. So this is phi a dagger I 1 minus a dagger I aj phi minus, and then again the square of the expectation value. And here we see that we annihilate and then annihilate the same particle again, so that is 0. So this is just the expectation value of the density matrix. This is not a 1, this is a delta ij. So this is given by delta ij and ij minus Nij squared. Now, if Nij is equal to delta Ij times 1 or 0 for occupied and empty orbitals, then this is either 1 or 0. The square of 1 or 0 is either 1 and 0. The density matrix is diagonal, so this delta has no problem, because when I is not equal to j, that one is also 0. And with that, the equation is fulfilled. Now, this requirement for your density matrix is exactly what we said that we have when we have a single slater determinant representable state on a natural orbital basis. So on the natural orbital basis, your density matrix is diagonal and the state is single slater determinant representable and thus uncorrelated when the occupations are exactly 1 and 0. Such that we can indeed conclude that uncorrelated states have no charge fluctuations on a natural basis. Now with that we come to the next statement that we want to show, and that is relate correlations to entanglement. When we talk about entangled states, we are thinking about having your many particle state and being able to separate it in two parts and see if each part can be described independently of the other part. Now, you can have entanglement in real space, but in principle you can talk about any basis set that you like within your Hilbert space. You don't have to separate in position, you can separate your state in momentum and see if states with different momenta are entangled or not. So we start with a one particle basis. And let's call this A, given by the states where we create particles with quantum number 1 up to the states with particle and quantum number n. So we have n one particle basis states. Now we define two subsets, B, where we create the state 1 up to j, and we take the subset C, where we take the particles j plus 1 up to n, such that the union of B and C gives you the set A. Now our state is unentangled. If we can describe the many particle state as a product of the state in Hilbert space B times the state in Hilbert space C. Now if we go to the natural orbital basis for an uncorrelated state, then we find that our many particle wave function is given by the product of all occupied states, where we create the occupied state out of the vacuum. Now for such a state we can definitely define two subsets, and actually any combination that you can make of the occupied states is allowed to be taken as a subset, and on that subset you can write your wave function as a product. Actually the wave function is written as a product of all single electron states that we have. So indeed we find that an uncorrelated state is not entangled on the natural basis, meaning that any subdivision of the natural basis gives you a state that is written as a product wave function, or the symmetrized product wave function on these subsets. and therefore not entangled. Last but not least, I want to have a look at mean field theory. And discuss a little bit what can be done and cannot be done on a mean field theory level with respect to correlations. Well, on a mean field theory level, your Hamiltonian is given as a single creation and annihilation operator. Now we can always make a unitary transformation diagonalizing the matrix epsilon ij, such that your Hamiltonian becomes a sum over, well, if we have a periodic system, a crystal momentum, over the eigenorbitals of your one particle Hamiltonian. These are the natural orbitals. Which means that all states that we have within a mean field level, all eigenstates of the Hamiltonian that we have on a mean field level, are uncorrelated. Now, if you now want to describe a system where we have correlations, for example, if you think of a quantum computer, then you have to use the correlations and the entanglements between states to be able to allow to do quantum computing, then you will never be able to describe this on a mean field theory level. This is not a problem of not having the right potentials within your mean field theory. This is just the very fundamental aspect of quantum theory, that in quantum physics you are allowed to make superpositions of states, and these superpositions are very fundamental. You cannot just rotate them away by making basis formations. At least not all superpositions can be rotated away by making basis transformations. And what is not rotatable away is what we call correlations, and that will never be capturable on a mean field theory level. Now, if you think about methods like density functional theory, there we have a correlation energy. And in DFT, people started to think about not describing states with wave functions but with densities, and in principle that is exact and that can be done. So once you then introduce Kohn-Sham orbitals to represent this density on the basis of a state, then you might say, hey, but that is a mean field theory where we definitely have some correlation energy. Now, there are two answers to this. One is where you say, yes, but the Kohn-Sham orbitals are not physical, they are just mathematical constructs, and you should not treat them as anything where you can put in physical interpretation. The other one would say that's perfectly fine. You can indeed have some correlation energy in density functional theory. Then your electrons are correlated. But what we do is, when we introduce the Kohn-Sham orbitals, is make some effective new quasi-particle. And this effective new quasi-particle moves in a potential. And these quasi-particles are definitely uncorrelated. So we capture some of the correlation energy that you have between the electrons, but in the end the quasi-particles that we discuss here are uncorrelated. Now, if you want to use density functional theory as a starting point to make correlated methods to describe correlations, it is the second interpretation of your Kohn-Sham orbitals that you take, which is in line with what you do in Hartree-Fock, for example, where you also generate an effective quasi-particle moving in a potential. Well, in Hartree-Fock, the relation between the quasi-particle and the electron might be easier than in density functional theory, but in both cases you can make clear prescriptions how you go from the mean field theory, which density functional theory on the basis of Kohn-Sham orbitals then is, to the exact solution, including correlations, which then need the entanglement between your electrons or allows you for charge fluctuations in your system. And of course, instead of looking at the charge that fluctuates, you can have a look at spin fluctuations or other kind of fluctuations. And on a mean field level or for uncorrelated states, you can always make a basis rotations such that they disappear. So these are then the trivial fluctuations or the trivial entanglement instead of the real entanglement that some systems have. So I hope to have given you some overview and some definition of what we mean when we say that a quantum system is correlated. And in the next video I will start with a hydrogen molecule and give you then an example where we see the correlations. This is also called a Hubbard dimer, and then afterwards we'll go to a Hubbard model and see how correlations play an effect there. For now, thank you very much, stay healthy, we see each other later.